Okay, there we go. Okay, really quickly, can we give a round of applause to Jasmine for all the hard work she's been doing with the expo and the lab? Okay, so I'm here to present to you Project Pepper. Now, Pepper stands for Project Engineered Plant Production for Expedition Research. This has been a 2-year-long research project where last year we focused more on building a physical prototype, and this year we focus more on doing research and kind of expanding on our previous design. So quick introductions. I'm Nabil Alum.
Hi, I'm Julissa Brunk.
Hi, I'm Diana Encinas. And I will be telling you guys about the problem that we focused on for Project Pepper. So currently nearly all food on the ISS is packaged in freeze-dried packages, and it is very high cost to bring food to the ISS, which limits the availability of food, and it is highly processed and unappetizing. Here are some statistics from NASA. 10 to 15% body mass reported lost by ISS crew members, 2% bone mass lost per month an astronaut is in space, and 25 to 30% less food consumption than before missions. These are obviously life-threatening concerns, so it is something that needs to be addressed. Our previous solution was a hydroponic system designed to grow fruits and vegetables on the ISS with a pump system that we used to control the movement of the air and water to get to the roots. And in a traditional hydroponic system, the air would flow upwards to the roots to provide the oxygen. But this isn't the case because it is a microgravity environment, so that's why we decided to use a pump system instead. This, however, didn't work because the pump system complicated the design. It increased its cost by adding weight to the prototype, and it increased risk of failure. It added unnecessary electronics and additional tubing, which we ultimately decided to remove completely so that the plant roots had more room to grow. And our team was unsure if the air bubble would also collect near the roots. Oh, it doesn't work. Okay. Well, this is a test ran by NASA where they put air in an air bubble and it created a ripple effect. You can go to the next one. And then this is a second test they ran where they added water into the water bubble and it created a bubble within the bubble. And this led to many questions.
Okay, thank you, Diana. So, did you want to talk more about the research?
This added more questions. Will our design cause additional air pockets to form? And will the roots cause these air pockets to burst or collect as it was shown in the video? And can we experiment this in space? Yes, we can. There was a CubeSat option that was explored, but later we did not pursue due to funding. And now I will pass it on to Nabia to talk more about her research.
Okay, thank you, Diana. So as she mentioned, one of the bigger problems that we were facing is that we didn't have a good understanding of how air bubbles worked in space, and we quickly realized that we were running into the fuel tank problem, which I know this video isn't playing, but essentially what's happening is that the air bubbles would get trapped in the tank and then cause the engine to burst in and out, which is clearly not something you would want. NASA has already solved this issue, and they've used capillary action and surface tension to kind of push the fuel towards the end and give the engine more of a constant flow. So kind of inspired by their solution, we thought, how can we implement this into our project? How can we also use capillary action and surface tension to move the water where we want it to go, like near the roots? So we decided to use a porous material to kind of mimic the solution that NASA has solved. It's like echoing. This porous material essentially would get absorbed with plant food and water, and then the roots would absorb that, and then it will also get enough oxygen it needs for the plants to survive. The porous material we ended up deciding on was rock wool and coconut coir, but in the end we ended up deciding on doing rock wool due to its hydroponics, water retention, insulation, and aeration, but also because of its pH stability, which ended up being like a huge factor into why we chose rock wool, because we later found a 2010 NASA article. It was 80 pages long, but essentially what it was that they were testing and trying to grow plants in rock wool and coconut coir, but because coconut coir has a low pH stability, the plants ended up dying. The rock wool did end up surviving, but both of them failed due to crystallization that formed on the surface layer. What they were doing is they were using a dropper which was mixed of plant food and water, and they were dropping it along these cubes. Eventually the plant food kind of settled at the top and it caused crystallization, so this plant eventually ended up dying due to overnutrients. So our new research question was, how can we prevent this crystallization from happening at this top surface and also make sure there's an even dispersal of plant food within these rock wool cubes? So I'm going to pass it off to Julissa to talk about our solution.
Yeah, Yeah, thank you, Nabia. So we're going to run an experiment with three different conditions. The first is our control, just a mister on bare plant roots, and this we're expecting the plant to grow successfully. This works great on Earth. We can't actually implement this solution in space because the water and air won't flow as it normally would on Earth, but this will serve as a good control. And then next we'll test rock wool with a water dropper. This is going to be exactly what was done in that NASA study. So we're expecting the same result, that the plant will grow at first, but eventually the accumulation of nutrient crystals will kill it. And lastly, we're testing rock wool and a mister system to disperse the water, which will be drawn through the rock wool with capillary action into the roots. And this we're expecting the plant to grow, and this even distribution of nutrients will prevent these crystals from forming. Yeah, so this is our space design of if we were actually going to send this up to the ISS. So at the top you can see it's a pretty standard hydroponic system, just grow lights with the plant, and those roots are anchored into the rock wool so that it can draw up humidity and water from the humidifier down below. And the humidifier is a fan attached to a wicking material which draws water up from an expandable water tank. And that's important because if we used a typical rigid water tank, as water's drawn out of it, air bubbles would form to fill the empty space, but we don't want to introduce air into the system in that part, so we use an expandable water tank that can just contract like a balloon as we pull water out of it. And yeah, this is a CAD model of our design. That mesh material at the top is the rock wool that will draw the moisture and nutrients into the plant roots. At the bottom, we have the expandable water tank, and then we wanted to include a manual on-off switch just in case something goes wrong with the sensor. It can be controlled manually so that the plant won't die and the experiment can continue. So the next steps for our project are to run this experiment that I described once our necessary materials arrive. Next, depending on the data that we interpret, we'll determine which water delivery mechanism was the best as far as high plant growth and minimal crystal formation. Next, we will improve on our design, prioritizing cost and weight efficiency. Every pound that's shipped up to the ISS is extremely expensive. It takes a lot of fuel, so really the best way to keep costs for our project low is to make it as light as possible. And next, we'll run a longer experiment to determine long-term plant viability and eventually use a CubeSat system to test our system in microgravity. Thank you. Are there any questions? Okay, great. Thank you, guys. Ooh, okay. I think that throughout the 2-year lifespan of the project, for me, the biggest challenge was learning how to build something physical when we were making our prototype last year, because I'd never done anything like that. I'd never used a power tool before, so that was a really big learning experience. What about you guys?
Yeah, I would say just the reiterations of experimenting and researching and seeing what works and doesn't work, as it's in a microgravity environment, so we don't have gravity, so we have to figure out how it would work without obviously gravity's input on it.
Kind of following that, I know Zach, he kind of explained it's kind of difficult to see where the project needs to go, because there's a lot of different pathways we could have taken this project. We could have done a CubeSat, we could have fixed our original design. There's a lot of things we could have done. We could have just applied for NASA competitions, done something like that. So we kind of switched our directions a lot, and it's kind of hard to figure out which pathway to take. So I'm glad we ended up choosing this and trying to do more research and see if this is a possible solution that we can pursue.
And just for our audience online, can you guys, if it hasn't already been said, tell us what year you are and then what your majors are, because this is very interesting.
Okay. So I'm Nabia. I'm a third year studying electrical engineering.
I'm Diana. I'm a second year and I'm majoring in kinesiology.
And I'm Jalissa. I'm a junior studying biology.
Thank you.
Thank you.
Thank you so much. Awesome. Next we have, let's see.